The universe is a vast, ancient library, its stories written in the language of light and gravity. For millennia, we have been confined to our own small section, reading the tales of our sun and its family of planets. But every so often, a book from a distant, unknown shelf arrives. A traveler from another star system, carrying with it the primordial script of its origin. This is the story of one such messenger, an object that didn't scream for attention, but whispered a profound truth about our galaxy. Now, let's turn our telescopes toward the data and decode this cosmic mystery. The night of July 1st, 2025 was like countless others for the robotic eyes of the Asteroid Terrestrial Impact Last Alert System. ATLAS, a network of telescopes standing sentinel on the volcanic slopes of Hawaii and in the clear skies of Chile and South Africa, scanned the darkness, hunting for near-Earth objects. Its software, honed to detect motion against the static backdrop of stars, flagged a new, faint smudge of light moving with purpose through the constellation of Lyra. In the dry language of astronomical logs, it was just another transient object. But as automated alerts reached astronomers across the globe, a quiet, methodical pursuit began. Follow-up observations from larger instruments confirmed what the initial data suggested. The object was fuzzy, surrounded by a tenuous atmosphere, a coma, and it was already sporting a faint but developing tail of gas and dust sublimating from its surface. This was, in every observable way, a comet. Yet, as observatories pooled their data and refined its trajectory, a startling fact emerged from the calculations. When we plot its path, we see it wasn't an ellipse, the classic closed loop of an object bound to our sun. Instead, its trajectory was a distinct hyperbola, a path of entry and exit. This celestial wanderer was not from our solar system. It was an interstellar visitor and was soon designated 3I/ATLAS, the third such object ever confirmed. And then, a strange silence. There were no sensational headlines, no feverish news cycles debating alien origins. The public, whose imagination had been captured years earlier by the enigmatic one I/Oumuamua, barely registered its arrival. Oumuamua was a cosmic enigma, a bizarre, elongated, tumbling shard that defied easy classification. It accelerated away from the sun without any visible cometary outgassing, an anomaly that, in the absence of a definitive natural explanation, left a sliver of room for speculative theories of extraterrestrial technology. It was a scientific puzzle gift-wrapped in high-stakes mystery. 3. I/ATLAS, by contrast, seemed to offer no such intrigue. When you look at the initial spectroscopic data, you see the familiar fingerprints of water ice, carbon monoxide, and silicates, the very building blocks of the comets born in our own Oort cloud. It presented itself not as a mystifying alien probe, but as a comfortingly conventional comet. It was this very normalcy that paradoxically became its most puzzling feature. Why would a visitor from another star system so perfectly mimic the objects from our own? It seemed the universe had sent us a postcard from a neighbor, only for it to look identical to the scenery in our own backyard. For the scientific community, this wasn't an ending, but the beginning of a far more subtle and profound investigation. The lack of a flashy, headline-grabbing anomaly forced us to look deeper, to scrutinize the one detail that didn't quite fit the mundane picture: its velocity. It was moving just a little too fast, a whisper of a clue that its journey had begun in a place and at a time far more extraordinary than we could have initially imagined. That single subtle clue, its speed, became the focal point of the entire investigation. In astrophysics, an object's motion is its autobiography, written in the language of vectors and orbits. To decode the story of 3I/ATLAS, we had to look beyond its simple passage through our solar system and place it within its grander galactic context. When an object enters our system, we first measure its velocity relative to our Sun. But this is a parochial viewpoint, biased by our own star's 230 km/s journey around the Milky Way's center. To understand a visitor's true origin, we must calculate its speed relative to the local standard of rest. An imaginary point moving with the average velocity of all the stars in our immediate cosmic neighborhood. An object ejected from a nearby star, a sibling from the thin disk of the galaxy where we reside, should have a relatively low velocity with respect to this local average. It would be like a car changing lanes on a vast highway. Its relative speed is small. But when we performed this calculation for 3I/ATLAS, the results were astonishing. Its velocity relative to the local standard of rest was immense, far higher than that of either Oumuamua or the second interstellar visitor, 2I/Borisov. It wasn't just changing lanes. It was a projectile fired from a completely different part of the galaxy, on a trajectory that sliced down through the galactic plane at a steep angle. Tracing this trajectory backward, we found it didn't originate from any known nearby star or stellar cluster. This was not a neighbor. This was something else entirely. To grasp the significance of this, you have to visualize the architecture of our Milky Way. What we typically think of as the galaxy is the thin disk, a bright, flat, spinning plane of gas, dust, and stars, including our Sun. This is a dynamic, youthful region where stars are actively forming. Surrounding this, however, is a much older, more diffuse structure, the thick disk. The stars of the thick disk are ancient, billions of years older than the Sun. They were forged in a much earlier, more chaotic era of the galaxy's evolution. As a result, their orbits are different, more eccentric, more inclined, and they move with much higher average velocities. They are the galaxy's old guard, ghosts of a bygone epoch. The extreme speed and inclined trajectory of 3I/ATLAS were a direct kinematic match for this ancient population. The current leading hypothesis is that this comet was not just from another star system, but from a star system in the Milky Way's thick disk. It was born billions of years before Earth, in the protoplanetary disk of a star that has long since lived out much of its life. Billions of years ago, a gravitational nudge from a giant planet in its home system ejected it into the lonely dark, and it has been wandering the galaxy ever since, a preserved relic of a primordial era. This realization dramatically recontextualizes our other interstellar visitors. 2I/Borisov, discovered in 2019, was, like Atlas, a comet that appeared compositionally familiar. However, its kinematics were gentle, fully consistent with an origin from a thin disk star system like our own. It was a peer. Oumuamua remains the ultimate outlier, its origins a complete blank. 3I/ATLAS, therefore, established a new category. It demonstrated that the population of interstellar objects is not a monolith. It is a diverse census, sampling different ages, different environments, and different epochs of the galaxy's history. This presented us with a beautiful scientific paradox. The comet's motion screamed of an ancient, exotic origin, yet its chemistry whispered of a comforting familiarity. Through the precise art of spectroscopy, splitting the faint light reflecting off its coma into a rainbow of constituent elements, we found the signatures of water, carbon, and silicates. these are the very same raw materials that built our own solar system. The profound implication is that the fundamental building blocks for planets have been widely available and remarkably consistent for billions of years across vastly different galactic environments. The chemistry that allows for the formation of worlds like ours is not a recent or localized phenomenon. 3I/ATLAS was no longer a boring comet. It had become a time capsule, a piece of interstellar archaeology delivering a sample from the galaxy's distant past directly to our telescopes. It was a silent messenger, and its message was just beginning to be understood. The discovery of a single ancient artifact can rewrite human history. The discovery of 3I/ATLAS is doing the same for our cosmic history. It fundamentally transforms our perception of the space between stars, changing it from a sterile void into a crowded repository of galactic memory. The detection of 3 distinct interstellar visitors in just a few years, with our current limited technology, is a profound statistical clue. It tells us that these objects are not rare celestial oddities. They are ubiquitous. When we extrapolate from these few data points, the numbers become staggering. For every star in the Milky Way, there could be trillions of cometary and asteroidal bodies drifting unbound through the interstellar medium, a ghostly sea of wandering worlds. Our solar system is perpetually flying through this cosmic rain, a constant stream of messengers from distant shores. This realization has opened an entirely new field of study: interstellar archaeology. For the first time, we are not limited to studying the remnants of our own system's formation. We can now directly sample the building materials of planetary systems from across the galaxy and, as ATLAS has shown, from across cosmic time. By capturing the light from these fleeting visitors, we are analyzing the chemistry of protoplanetary disks that are younger, older, and in entirely different galactic environments than our own. Each new visitor is a chapter from a different book in the galactic library, telling us whether the ingredients for planets, and perhaps life, are universal, or if every star system follows its own unique recipe. This reshapes our answer to the most human of questions. Where do we fit in all of this? We are no longer inhabitants of an isolated island. The galaxy is a single, sprawling ecosystem where the seeds of creation are exchanged between stars over billions of years. The discovery that the raw materials of our world are mirrored in an ancient relic from the thick disk connects our own existence to the deep, primordial history of the Milky Way. We are not a cosmic accident, but the product of physical and chemical laws that appear to be astonishingly constant and widespread. And we stand at the threshold of a revolution. Soon, the Vera C. Rubin Observatory in Chile will begin its legacy survey of space and time, imaging the entire visible night sky every few nights with unprecedented depth. Its vast digital eye is predicted to find not just one interstellar object every few years, but dozens. The quiet trickle of information will become a flood, allowing us to build a true census of this wandering population. We will move from telling the stories of individual objects to writing the collective history of galactic formation, one interstellar visitor at a time. The quiet arrival of a seemingly ordinary comet has, in the end, given us one of the most extraordinary gifts: a new window onto the cosmos. The long silent journey of this ancient comet through the vast star-strewn darkness of the galaxy reminds us that the universe is always speaking, its stories carried on the gentle currents of gravity and time. We have only just begun to learn the language of these interstellar whispers, but with each new visitor, we come to understand our own place within this grand, interconnected cosmic chronicle just a little bit better. Our exploration of the cosmos is ongoing, Subscribe to Cosmic Chronicles to ensure you don't miss our next investigation into the universe's greatest mysteries.